This video is going to help you learn how to simplify radicals, but before we can really look at simplifying radicals, we need to understand the terminology associated with radicals. So I've drawn a picture for you. The little symbol that looks sort of like a big check mark is called a radical. You have an index, which is kind of the little small number written in the V part of the check mark. Is called the index, and then the expression underneath the radical is called the radicand. Now, one of the radicals that we deal with most often in algebra is the square root, and typically with a square root, the index would be 2, and it's usually understood and not written. But if it's anything else besides 2, you'll see a little small number written there. Again, radicals are very much like fractions, and they should always be simplified. Well, how do you know if a radical is in simplest form? There are basically 3 conditions. 1, there are no perfect roots of any factor left under the radical. There's no fraction under the radical, and there's no radical in the denominator of a fraction. And the rule, the guideline in algebra that allows us to do this is that the root of a product is equal to the product of the roots. If you have a multiplication problem under the radical, basically this is telling us that we can break it apart into individual pieces. It's also true that you can do that with quotients or fractions as well. There are various methods for simplifying radicals. One is to use perfect roots, but this requires that you're familiar with perfect roots like the perfect squares, 4, 9, 16, 25, and so forth, or with perfect cubes like 8, 27, 64, and so forth. So if you're familiar with those and you feel confident, you basically are going to identify the perfect root that is a factor of the given value, and then you're going to have to factor it out or take it out of the radical. The easiest way to deal with the variables or the letters is to take the exponent on the variable, divide it by the index. Any whole units are removed from the radical, and any remainder units are left under the radical. A second method is you can actually do factoring. You can simply factor the given value and then look for sets of numbers that are equal to the index. If you have a full set, that means it's perfect and it gets removed from the radical, and any leftovers or singles have to remain under the radical. And you follow the same guideline there for the variables as well. And I'm going to try to demonstrate both methods as we look at some examples together. So example number 1 here on this particular problem looks pretty straightforward to me. It's the square root of 36, and I recognize 36 as being a perfect square. I have an understood index of 2, so I have to think to myself, what number times itself is going to give me 36? And it happens to be 6. Now again, if I break this down, if you want to use the factoring method and you don't recognize that as a perfect square, I can break this down and think, okay, what times what is 36? Again, I could think it's 4 times 9, and then I can say, okay, 4 is 2 times 2, and 9 is 3 times 3. So in factored form, I have 2 times 2 times 3 times 3. Then I want to look for sets of 2 since I have an index of 2 that's understood. Well, I have a set of 2s and I have a set of 3s. If I remove a 2 and a 3 from underneath the radical, that still does give me 6. So again, I can approach it in either format. It just depends upon which one you feel more confident doing. The second example, I have an index. Notice you have an index of 3. So now I'm asking myself, what number times itself 3 times would be 64? Well, I may not recognize that one as easily. It is, if you go back and look at the list I provided you on the previous slide, it is actually a perfect cube, as we would call it, and it is 4. But again, if you don't recognize it as being a perfect cube, you can actually begin by breaking it down into the factors. You could have 8 times 8, and then 8 would be 4 times 2, or 2 times 4, whichever way you want to look at it. 4 would be 2 and 2, and 2 and 2. So ultimately, I have 2 times 2 times 2 times 2. So I have a string of 4s, or string of 2s, excuse me, and I'm looking for sets of 3 because my index was 3. So I have, there's one set of 3 and a second set of 3. So I'm going to release 2 2's, and 2 times 2 is 4. So the cube root of 64 is 4. Okay, then let's look at number 3, 24. I don't recognize 24 as a perfect square. So I want to think about what numbers it breaks down to. And I'm going to do this one a little bit off to the side instead. I recognize 24 as 4 times 6. And then I could break that down further because 4 is 2 times 2, and 6 is 2 times 3. Since I have an index of an understood 2, I'm looking for sets of 2. So I have one set of 2's. So it's going to get released. The other 2 values have to stay underneath, which is 2 times 3. So in its final form, 24 is 2 on the square root of 6. The fourth problem is the cube root of 24. I did this on purpose so you can kind of see the difference between the two. With 24, again, we know that it is 4 times 6, or breaking it down further, we have 2 times 2 times 2 times 3. And I'm looking for a set of 3 since my index is 3. So there is a set of 3 2's. So the 2 gets released. The 3 has to stay under the radical. So the cube root of 24 is 2 on the cube root of 3. I'm mainly focusing on square roots and cube roots because those are probably the two that you'll see most often. With the square root of 49, if I think about it, I'm going to break it down for you so you can see it. We have 49 is 7 times 7. X to the 4th would be x times itself 4 times. Y to the 6th would be y times itself 6 times. Again, it's a square root, so I'm going to be looking for sets of 2. So I have a set of 7. I have 2 sets of y's, and then I have 2 sets of x's, excuse me, and 3 sets of y's. So I'm going to take out a 7, 2 x's, and 3 y's. And if you'll notice, 4 divided by the index of 2 is 2. 6 divided by the index of 2 is 3. Here's your answer: 7 x squared y cubed. All right, let's look at the next one. Square root of 63, x to the 5th, y to the 7th. Again, if we think about breaking this down as much as we can, 63, let's see, go up here and do some work. 63 is 9 times 7, and 9 is 3 times 3. So I have 3 times 3 times 7. Then I have 5 x's, and I have 7 y's. 7. Okay, had to squeeze them in there. All right. Now, again, because we have a square root, we're looking for sets of 2. So let's say I have a set of 3's. I have 2 full sets of x. I have 2, 3 full sets of y, but there are some leftovers. So anything that's a full set gets released. So I get a 3, and 2 x's, 3 y's, but then left under the radical I have a 7, 1 x, and a y. And again, if you'll notice, 5 divided by 2 is 2 with 1 left over. 7 divided by 2 is 3 with 1 left over. So this is the final answer, 3x squared y cubed times the square root of 7xy. Right, a couple more. Let's look at a couple of cube roots. We have the cube root of 125 x cubed y to the 12th. Again, if we think about breaking this down, 125 is 5 times 5 times 5. Then we would have x 3 times and the y 12 times. 6, 7, 12. Okay, I'm trying to squeeze them all in there. Make my little radical symbol long enough. There you go. All right, now we're looking for sets of 3. Since it's an index of 3, we have a set of 5s, a set of x's, and 1, 2, 3, 4 sets of y's, although I left one off. I miscounted. Okay, so I need one more. All right, so that means I have a perfect sets. They get released. So I have 5x, y, and I had 4 of those. So it simplifies to 5xy to the 4th. All right, and the last one, cube root of 16x to the 8th, y to the 5th. Okay, so let's see what I've got. I would have cube root, let's see, 16, if I do some scratch work up here, is 8 times 2, and 8 is 4 times 2, and 4 is 2 times 2. So I have 2 times 2 times 2 times 2, have 8 x's, 1, 2, 3, 4, 5, 6, 7, 8, and 5 y's. 1, 2, 3, 4, 5. Again, I'm looking for sets of 3 since my index was 3. So I would have one set, a full set of 2's. I have 1, 2 full sets of x's, and 1 full set of y's. So they get released. So I have a 2, 2 x's, and a y. And then I still have pieces underneath. I have a 2, I have 2 x's, and a y left underneath. Okay, again, notice 8 divided by 3, 8 divided by 3 would be 2 with a remainder of 2. 5 divided by 3 would be 1 with a remainder of 2. Excuse me, I got a little error there because I miscounted again. Sorry about that. Should be 5 y's here, not 4. Okay, so your final answer is 2x squared y times the cube root of 2x squared y squared. Okay, this concludes the video on simplifying radicals, where there's going to be a second video to discuss how to rationalize the denominator. How do you deal with the problem when there is a radical in the denominator?